Okay, in today's lab, we're gonna swing some masses around in a circle and find the, using the tension, we're gonna find how much they weigh, theoretically. The masses we're gonna be using today is gonna be a 10-gram mass and later on a 20-gram mass, but I'm not gonna bother filming that, it's the same process. How this is gonna work is we're gonna use this apparatus here where the mass we're hanging, as I said, starting with 10, I'm gonna go and attach to this arm. This can move freely and is attached to this cable. Now the cable, which as I see, you can see it move freely. The cable is attached to this force meter. What that force meter is going to do, and I'll move this for a second. Chris can't read. So I can't get an angle, you can see it, there you go. Is going to read the tension in the cable. When I pull this over, you get a higher value. When I let go, you see a smaller value. And that'll just say what tension that cable has to keep it on a circular path. Now this will be spinning in a circle, so I want to make sure everything is balanced. When this spins, it's going to be at a radius of about 70 millimeters. So I'm going to attach a second mass that'll be fixed in place at that same spot. This is just for balancing and is not actually included in any of our data. Okay, so that's at 70, that's at 70. Okay, now, what else is going on here is at the bottom, it's kind of hard to see, but there's this little piece hanging off the bottom of this one. That's going to go through a photo gate here, and we'll count how many times it passed through the photo gate. We're going to use our smart timer again today, and the smart timer is going to record how many times that passes through in 60 seconds. AKA, how many revolutions does it make in 60 seconds? AKA, what is the angular velocity in RPM? So, we're going to do this for a series of speeds. I'm going to start by just doing one. And how we're going to control the speed is by controlling the voltage on the motor on the bottom. So I'm going to bring this up to 3 volts. I lied. I'm going to 4 volts. This is 4 volts right here. As you can see, it's spinning, and we now have a value for the tension, which once again is new and possible to read. You can see it in that view. You can see the tension is now like it's about 0.56 as opposed to 0 when it wasn't spinning. If you want, we can go back to that. About 0. I'm going to 0 it again. Now it's 0. So going back to 4 volts. It's about 0.5. And now I'm going to measure the angular velocity in RPMs. To do that, as I said, we're just going to count how many times that piece passes through in 60 seconds. So I'm going to grab this guy here and just turn it on. Okay, there we go, 227. That means it went around 227 times in 60 seconds, or its angular velocity is 227 revolutions per minute. That angular velocity we can convert to radians per second, which we will need to do to get what the angular velocity is. I will give the series of angular velocities in revolutions per minute, and I'll also give the tension readings of this guy. What you're going to do is take your angular velocities and convert them to radians per second. Once you have in radians per second, you will square it. And then you're going to make a graph. You are going to graph T versus omega squared. This tension versus the angular velocity in radians per second squared. Why that graph is useful, you can see in the lab yourself. I expect you to read it. All for the record, all is going to be the radius, how far out this guy is. So I'll post that in a little bit with the data.